The chat. Okay, I got the chat. Okay. Does my chat show up on the screen just as an aside?
What do you mean? Like
I have the
or you have it?
chat. Well, if you're not seeing it, then the answer is no. Okay, cool. Okay, so if I'm having little sidebar conversations, y'all ain't seeing me doing that.
Oh no, we just see your slides.
Okay, cool. All right, so just kind of checking in, just some reminders. Project 2 is due next Tuesday, Star Wars Day. So we're going to be celebrating that. We got a couple Star Wars memes in today's lecture. You know, you just had to get it in. But yeah, Project 2 next Tuesday, Homework 2 next Thursday. So hopefully you guys have at least started, made progress, everything like that. As always, follow along. We are going through a brief coding exercise today, not a whole lot, but I just kind of wanted to consolidate some of the stuff we didn't explicitly work through last time in terms of coding. So just making sure that you have pretty much all the code that you need to do Project 2 at this point. So we're going to go through that. But yeah, in terms of agenda for today, so I have some slides prepared on logistic regression, but I kind of feel like we've beaten that topic to death in lecture. I mean, you guys spent basically almost 2 lectures on that this week. So I have the content on the thing. I want it to be like a resource, but I'm kind of feeling that maybe that's not where our energies are best spent at this point in terms of homeworks and projects. So, you know, maybe we'll just kind of breeze through that. And then I did want to talk about SVMs. So because support vector or classifiers are also in project 2, but we haven't talked about that material yet. So I want to kind of deal with that. I want to talk about kernel functions, because that's also in project 2, and I think as part of the homework. Then I want to introduce the topics of bias and variance, because we've kind of hinted about those issues, and we've sort of flirted around the periphery with them, but we haven't really kind of done a deep dive on that. And so I want to talk about that. I want to talk about that in context of normalization, because again, that's in the homework, that's in the projects. We've begun talking about that in lecture, but I don't know to what extent we've really kind of delved into that in a good and thorough manner. So I do kind of want to do that. And I think that's what I got on the agenda for today. So yeah, how does that sound?
You're the boss.
Okay, well then let's dive in. So again, these materials are here, you know, again, in lecture. I think we've pretty, Majid, I think, did honestly a better job than I could, just kind of walking through the transition from thinking about models as predictive regressions to moving towards a paradigm of classification, and, you know, why sort of a linear regressor is not, it's really, you know, it's the round peg for the square hole for this type of thing. And then conceptually moving into a, you know, there are different ways of achieving classification. And we have already sort of learned our first one, which is looking at it in terms of geometric proximity. So KNNs, you know, looking at that as a means of doing classification. And this kind of introducing another paradigm for us, which is looking at this probabilistically. So, you know, and kind of changing the regression model into one that outputs predictions and you know, probabilities associated with them, rather than you know, actual values. So, and again, I think this has been done pretty thoroughly. Let's just have this as kind of a reference, but, you know, molding that within the logistic model that sort of gets that nice kind of compresses your data into 0 and 1. Kind of an interesting kind of background on this, that the sigmoid function was initially developed to model population growth in ecologies, because there's the idea that you can kind of, when conditions and permutations change slightly, you can get like exponential population growth. You may be at like a lower stage equilibrium, and then you may get that, you may actually then sort of level out a higher level equilibrium. And actually, we've seen this in aggregate. If you model human population growth over the last few hundred years with the advent of industrialization and whatnot, where we sort of actually got this kind of sigmoid-like growth where populations just exploded, but now hopefully are flattening out before we encounter ecological disaster. Fingers crossed, 50-50, we actually manage that. But kind of cool idea of like a cross-pollination of disciplines, that this was originally a mathematical model developed in ecological and population studies, and that we've kind of grabbed and taken over into like the computer science, machine learning space. So I thought that was kind of cool. And then again, just thinking about this outputting in terms of odd ratios and the associated probabilities. And then this is kind of the last thing that I kind of wanted to emphasize, because I think this is sort of an important conceptual model, which is if you think about, so remember when I said like for almost every classifier, it really does two things. The first thing it does is it learns a model of your data. It develops kind of a framework for understanding your data. And then there's that separate kind of activation function, decision function, something that says, okay, well, based on the information that's feeding into me, I have to output some kind of binary, assuming you're doing a binary classifier, I have to output, a 0 or a 1. And so, and ultimately, and so understanding that you have both these, you have both this probabilistic model generating a series of probabilities associated with classifications, but then there's that separate linear decision boundary that once you have that, once you have sort of, I think you define a threshold. And in the case of logistic classifiers, it's going to be a probability. So it may be 50%, 60%, whatever your threshold is that you're doing. And then that linear decision boundary is associated with sort of quadratic features of your things. So you can kind of solve for it that way. And I think that's important to note, because those are kind of discrete steps, that there is the probabilistic generation phase, and then there's the linear decision boundary that's associated with that. That once you have those probabilities, you can set a threshold, again, let's say 50%, and then everything that falls above that is labeled, in this case, 1 or 0. And honestly, pretty much the only reason I displayed it was I was proud of this meme. So that was a home cooked meme. No plagiarizing that meme. Got a few of those today. Rather proud of those. So I think that's kind of what I wanted to say specifically about logistic classifiers. And again, from a paradigmatic standpoint, this was a probabilistic model. I know in lecture we touched on another one in Bayesian classifiers, and that's something else we're going to cover explicitly in discussion too, because it's interesting. There's really only a handful of classification models that you can kind of back of the napkin do, Bayesian being one of them. And so as a kind of I don't know what's going to be on the exam, but at least in the past, Bayes was kind of a good question to ask in terms of model solving, because again, there really is only a handful of these that you can actually solve. KNN being one that you've already learned, but Bayes is another one that you can be given a problem and just sketch out a thing. So, yeah.
So,
oh yeah, sorry, go ahead.
If we're ever asked, like, is logistic regression a linear classifier? What would the answer be?
Yeah, so really good question. So it's, as I kind of note here, it produces a linear decision boundary. So generally it's sort of, it's classed under linear classifiers, even though the model itself is not, it's not a linear model. But because it produces a linear decision boundary, it sort of folds under there. But that would be, I think there's ambiguity, and really depends on how you define that. Like, it's not like, for instance, we're going to look at SVMs next, and there it very obviously is a linear model. But here it's really more of it's a nonlinear model that produces a linear boundary.
Okay.
Yeah. So I think if you were asked something like that, you would probably be given enough nuance to qualify an answer. So again, I think we've kind of beaten that particular horse to death. Just judging by the questions we've gotten in office hours and things, I think that's not really where people need much. But again, the material is there as a reference to kind of help with studying or exams or whatnot. So on to SVMs. And I'm right in saying Professor hasn't touched on SVMs yet, correct?
No, he hasn't.
Okay, cool.
He
So
just mentioned that they were coming.
okay, cool. All right, so then we get our little preview here. We're getting the early bird discount on SVMs. So if you think about kind of methods that you can use for classifying your data. So I think kind of this is sort of an interesting thing in that conceptually it sort of borrows from both a KNN and a logistic thing. In that, so remember with KNNs, we said let's look at proximate points. So if we have a data point, let's do a count of nearest points, and let's just do a majority rules for that thing. And that was the approach we took. And then of course, for logistic, we just kind of talked about how you use the probabilities to generate this linear decision point. Well, conceptually, there's another kind of approach that says, well, if my data is arrayed on a sort of sort of a multi-dimensional plane in such a way that you would assume ideally can be kind of divided in half. That assuming these classes are discrete, assuming that there's relative, that they demonstrate clear differences in terms of patterns, theoretically, I should be able to kind of cut these in half. And so, and this is an example here. If I'm looking at a two-dimensional space, I should be able to do a one-dimensional line that might be able to cut my data in half. If it's a three-dimensional space, I might be able to do a two-dimensional plane height that will cut that in half. And generally speaking, if I'm looking at data in n-dimensional space, I should be able to get some kind of divider in n-1 dimensions that will kind of cleanly cut it in half. And one thing, just to kind of make sure that we're sort of conceptualizing this properly, in this case, what are the dimensions? If I say, I'm looking at this in two-dimensional space, what are the dimensions that we're talking about here?
R2.
So it's a two-dimensional space, but I guess in terms of understanding the model, like in terms of inputs and labels, like what are my dimensions in this case? Features. Okay, good. Yeah. So Neil, you're exactly right. When we talk about dimensions, we're really just talking about features. So every feature you can think about as a dimension. So that's exactly right. And if you think about it, right, because there is, a certain value feature, if this is a two-dimensional space, will have an x1 value and an x2 value. So theoretically, if we have this data on this n-dimensional space, I should be able to cleave it in half in such a way that then I get this nice quadratic form equation. And that's essentially this hyperplane. And okay, sorry, there's a question on a target space as an additional dimension. Sorry, Neil, could you clarify what you mean by target space? Oh, the label. Yeah, so the label in that case would be your y value. So if you think about like y equals, mx plus b. So the y, I know like we typically talk about like x and y axes, but in this case, y would be separate from the dimensionality of your space. It's kind of a separate sort of dimension. But yeah, good question. Thank you for clarifying that. So, right, conceptually that makes sense. We develop this quadratic equation. It gives us this nice little line here. Anything above that line, we label one thing. Anything below that line, we label another thing. Conceptually very simple. Potential problem though. Even if we have a nice clean divider between our classes. So you see here this bottom graph here. We have our blue class and our red class, and I apologize to those who are a little color challenged. But we have
Yeah, it looks the same to me. I can't tell.
So you'll just have to take my word for it. This is one class up here. This is another class here. So we have a nice clean separation between them. The problem is, where do we draw that line? And to be more specific, you could have up to an infinite number of potential lines that will cleanly divide your thing. So how do you know which one to choose? So that's where the idea of support vectors okay. Support vectors come in. So the notion of the support vectors is, where sorry. Oh, okay. This was the key here. The trick that we want to try to do when we're selecting the line is, we want to try and choose the line that maximizes the margin between my two clusters, between my two classes. So the idea is, we want to try to give as much space between those as possible, such that if we get, points that are kind of near that decision boundary, we're sort of getting as clear a difference as possible. So that's kind of that's what our aspirational goal is here. And so this is a nice graphic that kind of showcases, if we have our separation here, we really want to try to get a line that just maximizes that difference. How do we do that? So the trick is, we only need to look at a subset of our total data set to do that. And that's what's known as the support vectors. So support vectors are essentially the points that fall nearest to the other classes. So if you think about like a KNN as needing to keep the entire data set in your model, and that's your model, here we're really just looking at the subset of points that essentially form that decision of how to maximize the margin. Then once your model has identified those support vectors, it then sort of tries to maximize the distance between them, and that resulting line is your classifier. So so we talk about like a linear classifier. This is a perfect example of precisely what a linear classifier is. So that's SVMs in a nutshell. Simple, easy, breezy, beautiful. We're done here, right? Not quite. So there are a few kind of there's a simplifying assumption we made here, which was that our data had this nice, clean separation here. The reality is that will almost never be the case. Our data is going to be messy. These labels will overlap. It'll be difficult to kind of get that nice, clean line between them. So how do we potentially address that? There's two strategies we can take. The first is a soft margins approach, which says, let's kind of look at this and let's still do this sort of linear separator, but let's accept the fact that maybe some classes will bleed over, and that's okay. We don't need a hard margin. We don't need a firm thing. We're okay potentially allowing for some error to creep in. That's okay. The second approach is kernel functions. And that is what we are going to talk about right now. Okay, kernel functions, which has nothing to do with the kernel or KFC, but 3 a.m., that seemed like a funny joke. So the whole notion of a kernel function is that we can take our current data frame, our current sort of set of data that are nonlinear separable. We can map that data into a new higher dimensional space. And in that higher dimensional space, we can achieve a linear separation. And that's literally exactly what a kernel function does. So if you look at this sort of being our initial data frame here, this is messy. Our border looks all balkanized and terrible, and like some politicians gerrymandered or up the wazoo. We just transform that, and we're going to talk about what that kind of looks like, how that works into a higher dimensional space. And then suddenly, oh, beautiful. We can get that nice, clean, linear hyperplane that we have so desperately wanted. Okay, Timothy in the chat has a question about, does this risk overfitting? Yes, it does. And this is kind of the trade-off. This is the interesting thing about with this method, is that sometimes, right, there's this, oftentimes this leads precisely to overfitting, and something like this looks terrible. And you're looking and you're like, my God, I have overfitted the heck out of this. But sometimes that's what you need to do. There's that kind of sweet spot where maybe to achieve a more optimal thing, you need to overfit a little bit because the model isn't robust enough to kind of handle that otherwise. Now, can you go too far? Yes, absolutely. And in fact, that's one of the risks of employing kerneling functions in general, is it can lead to overfitting. So, but that's, again, one of these ongoing themes in data science is that Goldilocks thing. Too much, too little. There's always that trade-off, and you don't really know oftentimes until you try it whether or not this is going to work or not. So you were probably, well, actually, let me pause there. Any questions so far? So that threw a
Lionel,
lot
could you
at you.
to the SVM slide, please?
Hmm.
I just had a question on the, like, defining the support vectors. So right here, like, it seems kind of to me like it's a bit of a greedy algorithm where it's trying to maximize that subset of sample space you have right there. So it's possible that even though you have a hyperplane that maximizes your support vectors there, every other dot is sort of flipped and you don't actually classify it well.
Okay, sorry, Brandon, I'm not following things. So you were saying this is sort of this greedy approach, which you could sort of, as you could see, and I'll be honest, I'm not actually sure the mechanics of how it's defined. But yeah, sorry. So you're saying a greedy approach for determining this?
So at least from my understanding, it looks like it's trying to maximize the number of blue dots in that little blue section and the number of red dots in that red section. But is it possible for us to wrongly set up our hyperplanes such that we maximize that area? However, all the blue dots in general are actually on the opposite side.
Yeah. So, okay. So great question. So, and maybe let me clarify. So you wouldn't, because this is our training data set. So you would never get a linear separation that would kind of mistakenly put all the blue training samples over here, for instance. But you're right to say that it's very possible that when we get our testing data, all of our testing labels will end up over here. Or maybe they will end up over, right at this border, maybe like this borderline right over here. And if we just did like a slightly sharper angled thing, maybe, we would classify all those test blue labels here. And now because we have done this approach, it's going to miss it. So in general, you're absolutely right that, we're using a heuristic in that we're saying we don't really necessarily know how our test data is going to perform relative to our training data. So the best thing that we can do is just try to kind of minimize the risk of misclassification by trying to maximize the margin. But it's a heuristic, it's a guess. We don't actually know that that's going to be the case. So you're absolutely right, assuming that that's what you were asking. Okay, awesome. So this is kind of the conceptual point that I want to work through, because if you're sitting there going, now what incarnation would cause simple dimensionality expansion to suddenly make my data linearly separable, you would not be alone. This is something that actually, when I learned it, it took me a while conceptually to understand why this tool worked. And when I first saw it, I was like, oh, okay, kernel function, blah, blah, blah. Didn't really get what I was actually doing with this. So eventually I found some examples that really helped. And this is, I think, a great example here. So let's say we have this data set here, and it's a single feature data set, and that has two classes associated with it. So I have my X1 feature, my two classes. Just eyeballing this, we can see very clearly that there is kind of a clear distinction here, right? We can clearly see that, if I could draw a circle around this interior here, I could get a nice, clean, perfect classifier. The problem is I can't do this linearly. There's no line that I can draw, no segment break that I can do. I guess in this case, it would be a value, right? Because this is a unidimensional thing. So there's no value I can choose that would segment this properly. But if I cast this unidimensional feature into a two-dimensional space, and I use this transformation function where I take the initial value and then I square the value. So essentially I'm adding a new feature, a second feature of x2, that is just simply the squared value of x1. My data now looks like this. And suddenly I can very easily draw a line that segments it perfectly. So in basic terms, that's exactly kind of what you're doing here. And I think, you know, the key point, yeah, so, okay, so there's an interesting question, why you are not just simply replacing it. And I think, well, that's a good question. I think probably the reason, well, if you just take the squared value, I think you still need your x1 to achieve the linear thing. Because if I'm just looking at this, I would get my squared values, right? This feature would just be stretched out. But you know, but I still wouldn't be able to achieve my hyperplane.
Well, I think if you just squared, like if you just said like, I don't know, x1 equals x1 squared, you'd end up with every value like of x1 squared, like less than 4 would be yellow, and anything greater than 4 would be blue, right? Because it gets rid of all like the negatives. So like
Oh, I see.
effective.
Yeah. Okay. Yeah, that's fair. Okay. So I think more generally, and so maybe that's why this particular example, so that's a limitation of this example. So thank you for clarifying that, because you're right. In this case, you could square it, and by getting rid of the negatives, you could set a linear point that would do it. So you're right. I think what is different about this is that you will not always have a pattern that by applying sort of a single dimensional change to it will suddenly make it linearly separable. You sometimes do need to cast it up into n+1 space in order for this to be possible. So like this is a non-numeric example of this where we have data here on a two-dimensional space. Clearly we can't get a linear divider here, but when it's cast into that n+1 space, we're able to get that hyperplane that cleanly does it. So I think part of it is, so there is this transformation side of it, but there's also the dimensionality expansion space, which is important to achieving that. So, and I think that's a limitation of this example. Maybe that isn't clear with the other ones, but yeah, thank you for calling that out. And there's another kind of element, and this is the other element that leads to overfitting, because we talked about relative density of our data. And that's another sort of thing why, so remember we said like expanding our features, expanding the dimensionality of our features will lead to overfitting, will lead to that sort of thing. And it's precisely the idea that as the density of your data decreases, the probability of you being able to achieve a clean separation increases significantly. And you can kind of see that here conceptually, right? If you look at here, you know, on a unidimensional frame, we're looking at sort of a 12 unit thing, and we're looking at 10 space. Suddenly here, by kind of expanding out into, I don't have the numbers out here, but you can see how from a density perspective, we have drastically lowered the density and spread these out. And as you continue to do that, as you take these into more and more features, you go from a two-dimensional space to a three-dimensional space and so on and so forth, the density just kind of exponentially decreases to the point where almost any data can eventually be cleanly separated. The problem, though, is that oftentimes you end up with a resulting model that looks like this. That's this just terribly mashed up, chopped up thing. So, and again, that kind of leads to the balance. Sometimes kerneling can be just the thing you need to get that perfect pattern. Oftentimes, though, it might overdo it. And again, I think the sort of the key point here, the key takeaway for like kerneling as a method is that this pattern was always there. It just wasn't approachable from a linear perspective. And so all we're just trying to do is by taking sort of that, by expanding the dimensionality in a certain, applying certain transformations, we're then sort of achieving that linear separability that wasn't available. And that's just in general, like when we talk about sort of data augmentation, feature augmentation, we're not inventing new data. We're not sort of manufacturing new data. We're taking existing information in our data set and we're just kind of recasting it into this higher dimensional space. So one of the things that you're going to see is that one of the options that you have for SVMs is you have different kernel functions, so different types of things. So we used a very simple thing where we just squared our values, and that was something that we did. Well, the truth is you have a lot of different options available to you, depending on what type of kerneling functions you want to do. And in fact, for our project, you're asked to look at one of those kerneling functions, RBF, which is the default kerneling function that's often used for these. And it's really, really good for handling data that is intrinsically nonlinear. So data that sort of really poorly fits a linear classifier, and RBF can be really effective. But there are other kerneling functions that you can also employ that would sort of better work, particularly with data that's more linear, as an example. So these are just kind of examples of data when you apply different types of kernel functions and different types of decision functions to it. So, and again, this goes back to the question I think that a lot of you guys have already kind of talked to about the trade-offs involved. So RBF, the reason that you don't always use something like RBF is it will very often result in overfitting. And when it overfits, this is something we're going to talk about a little bit, it just makes a model that can't be generalized. It's also worth noting that some of these kernel functions can be very computationally expensive, particularly when you're dealing with sort of larger data sets. So that might also be a factor that would influence your decision on what kernel function to use. Okay, so those are our support vector classifiers, and that is kerneling in a nutshell. Okay, coding example. Back to the avocados we go. Again, there's a link to it. And pull it up. You saw some of this material last week in the slides. I just didn't give it to you in codebook form. So everything you've seen here, I just want to kind of call out the stuff on the SVMs, and I want to call out the code for cross-validation, because I don't think I had given you that explicitly. I think I gave you screenshots of it. But everything else you've seen previously. One thing that I want to kind of explicitly do. So the first thing is you can, just like the logistic regression, the way to do this is very similar. You import your models, support vector classifier. You import a specific, you define a specific instance of it, you do your fit, and then you generate your series of predictions and you generate your score, which, as you'll remember, is the probability associated with a particular label. Now, here is an interesting thing that I want to call out specifically for SVC. You will notice that I set this parameter probability equals true. And there's a reason you need to explicitly do that for SVCs, particularly specifically if you're interested in doing if you're doing an ROC curve. And the reason for that is because remember how we said that our logistic regressions work with probabilities, and then our SVMs don't. Our SVMs, very similar conceptually to KNNs, they look at the geometric array of your data. And it's anything above this line is classified one, anything below it is classified the other. And there's no, right, that's a very kind of binary definitive state. There's no probabilities associated with that. It just is that. So, so there's no probability of that. And if I want to generate an ROC curve, so if you recall, I guess taking a step back, an ROC curve, remember, we were looking at our sort of our true positives against our true negatives as we lower our decision threshold boundary, right? So we have that notion being that we have probabilities of a label associated with our data. And then as we lower our decision for what we allow, if we start at 80%, 75, 70, 60, 50, we're going to sort of admit more and more true positives. We're also going to admit more and more true negatives as that time goes. And then theoretically, hopefully, we're admitting many more true positives before our true negatives. And so we get that nice kind of, I guess I'm not sure if I'm mirrored or not, but you get that nice curve where your true positives go like almost vertical, maybe admitting a handful of true negatives. And then as you sort of have maxed out your true positives, at that point, you start admitting your true negatives. And ideally, you get that area under the curve that approaches 1. So SVMs, because they're not probabilistic classifiers, because we don't generate probabilities with it, because it's this binary, either you are above or below, they don't intrinsically allow for ROCs, curves, as a metric. But good news is we can generate an ROC curve, and we can do it by setting this thing to probability equals true. So this is kind of a cool thing where it generates the probabilities, and it generates the probabilities by essentially cross-validating your SVM model. And rather than training a single model, it will train your model multiple times. And each time it will see kind of how the decision boundary sort of falls out, so that when you plug in your test data, it'll plug it into there and it'll say, okay, well, for these, let's say just an example, 10 models, 6 out of 10 times it classified it this way. So we're going to assign a 60% probability for it. So, and you will see this if you actually run your model. The default is probability equals false, because this is computationally very expensive, as you can imagine. But if you want to try and do that, you can run this model with probability equals false, and you'll see it'll run trivially, and then you can set it to be true, and you'll see there'll be a significant processing time associated with it. But again, in this instance, if you do want to generate your ROC curves, which for this project we do, you do want to make sure that you've set probability equals true. So otherwise, it just flows exactly the way we've discussed. You can generate your array of predicted labels using just the predict, and then you can do the score thing, which is you just apply your features, and you generate both the predicted labels and the predicted probabilities associated with them. And then everything else kind of flows from there. Any questions on how to code up an SVM specifically, or I guess just in general? Okay. Ba-da-ba-ba-ba, we're loving it. And then the other thing I want to talk about is cross-validation, because I did throw up the code last time, but I didn't give you the coding example. So now I'm giving it to you. So I won't go over in depth, but if you remember from last time, yeah, Mickey D's, you know where my head's at. I'm eating lunch, so you know where I'm going. So if you remember, we talked about cross-validation, and the idea last time that we'd introduced was that your model results were highly, highly sensitive to the particular way in which you had cut up your data between your training and your testing. And we were really interested in seeing how your model would perform more generally. And cross-validation was kind of a way of doing that. It was a way of saying, let's do a sanity check, and let's let's try and see, like, if we run this model multiple times on sort of different permutations of the data, how will the performance change over time? Is it the kind of thing where if you just happen to get the magical distribution of training and testing, you'll get perfect scores, and the rest of the time it's just a garbage dump? Or is it something that the performance tends to be pretty consistently high, such that it gives me confidence that whatever specific model I happen to use going forward, it'll generalize well, right? That was the idea of cross-validation. So to kind of help visualize it, I have some code here that you can kind of take a look at. So here I have an array of 12 values. I define a k-fold split of 4. and then I do my split, and then I just print it. So you can see here of my values. In this case, it chops it. My first 3 are my test, and the residual 9 are my training. Then, middle 3, and then the kind of the segment there, ladder 3, and then the final 3, and then the residuals being my training thing, right? So that's how kind of a k-fold work. It'll sort of systematically do that. And one thing I'll note here is that I have not turned on shuffling. So you'll remember something you could oftentimes do for your k-fold is shuffle the data. So right now, this is a nice ordered thing, and I wanted to do that specifically so you could visualize it. But here, I wanted you to kind of see this independently. I do this also for our data set here, just so you can see it. Note that this outputs the index values associated with it. So you can see like 0 through 4,562, and then picks up from 4,563 and goes all the way to the end, and so on and so forth. So that's just kind of visualizing how a k-fold works. Then we have the code for it. So we mentioned, sort of the way it works. First, we have define a particular instance of our model, which is essentially the instructions that we're going to do. So we take the model selection method, we define it specifically as k-fold, and then we input these parameters. So we have our random seed, we have the number of splits we're going to do, and we're going to turn shuffling on for it. So good question. So there's a question in the chat about whether or not we want to shuffle. It's generally considered good practice to do that. And the reason why is because oftentimes the data set that you receive is oftentimes input sort of chronologically. So, you're going to get, right, if you think about it intuitively, your earlier data points will be input earlier, your more recent ones will be sort of lower down. And you want to control for maybe kind of variance in your data across time. And so shuffling is kind of a good way of just randomizing it to make sure that there aren't kind of random patterns that emerge based on where the data is segmented. Because oftentimes there tends to be, chronologically could be a way of doing that. You could have your data sorted any other way, right? I mean, oftentimes you'll sort by certain features and not even be aware that you're doing that. And so this is a way of just ensuring that your data frame is truly randomized. But yeah, great question. So here I do a comparison thing. So I'm going to define an instance of a logistic regression. I'm going to define an instance of a support vector classifier thing, and then I am going to run both of them. I'm going to define another sort of array, which is my results. I run again that model selection, specifically cross-validation score, which gets that, my specific model, which I've defined, my data, my labels, and then my cross-validation strategy, which I've defined here. In this case, I run it for both, and then I just output, in this case, the results for both. So I can call this function log results mean. In this case, I output as a percentage, so I just multiply rather than a fraction, so I just multiply by 100, and I get my results. Also just set cross-validation to 10. Do a k-fold with 10-fold. So yeah, so good question. I think if you just set this to 10, you're probably okay. I think the reason you may want to define this separately is if you want to play with sort of additional parameters. But yes, I think if you just set it to be 10, I think it'll output as 10. But again, you won't, like if you want to do something like shuffles, or you want random seed, or you want to do any kind of other specifics, you may want to kind of define it explicitly. But yeah, I think that would work. So yeah, so you can definitely just kind of do that too as a simple thing. And I think for this project, you're probably fine if you do that. Yeah, good question. So I think hopefully this is pretty much the code you need for this project. I don't think there's really anything else that we haven't given you to do project 2. I mean, hopefully, to be frank, the code is not the interesting part of this class. I think the interesting part is the theory. And so we really don't want you bogged down trying to debug that. So, we obviously want you to learn how to do it and go through the motions, but we're not trying to trip you up in terms of debugging Python scripts. Where is my chat? Okay. Nope, it's not there. Okay, so I need to bring it to the. Okay, so that is that. So where are we up to with that? We did that. We did that. Okay, yeah, I just have this copied over. Blah blah. Okay, we did all that. Okay, so normalization time. So let me kind of take a step back and sort of ask a sort of a high level question, because we're just kind of taking on an assumption. I'll be like, yeah, your data is not always reflective of real world values. And we sort of know intuitively that's probably the case, but let's be explicit as to why that is. Why is it that this data set that I collect doesn't perfectly match up with the real world? And what might be the problems for that, right? Because this is kind of the, if you want to like the underlying core challenge that we have in both data scientists and really statistics. It's this idea that we're given this sort of, I use the term here, snapshot of the broad world, right? We're given this bucket of data here that is supposed to be reflective of the broader ocean of things, and we're trying to infer a pattern there that isn't necessarily the case. And so why is it that that bucket typically isn't? So I have a few examples here to work through. The first being the idea that, simply put, when we sample things at random, we're not necessarily getting a robust distribution. And you may end up getting, your random sampling may not align with the broader kind of distribution in the universe of data. So that's oftentimes the case. Another kind of important thing to note here, and by the way, you thought we were done with the birds in this class. We are not done with the birds in this class. We have not even begun to scratch the surface of birds in this class. But it's the whole idea of correlation not sort of being equal to causality. And I think it's kind of important here to sort of note that when we talk about sort of applying models, when we fit a linear regression to our data, I think there's an implicit sort of desire to say that that's a causal relationship, but the reality is oftentimes it's not. Oftentimes what we're really looking at here is saying that there is an association, there's a correlation, there's in general, a reality that these two features tend to sort of align and tend to kind of move together in concert, but they're not necessarily engaging or directly working with one another. And in general, what we really are doing when we fit a model to data is we are essentially, there's kind of like applying, if you think about math as a language, we're really applying sort of the language of math to data that we see to try and kind of describe a pattern. But in describing that pattern, you're not necessarily associating a causality with it. So it's, so again, it's important to note that we're saying, yes, these two features tend to kind of move in concert. There tends to be that relationship, but we can't necessarily say for sure there's causality. And there's a lot of really interesting work done on determining causality. I don't know if you guys are familiar with Judea Pearl and his work, but he's kind of been at the vanguard of thinking through like causal inference and how you actually kind of take that step from correlation to causality. And just fascinating work. I understand almost none of it, but it's really, really cool work. And if you have a chance to kind of check out some of his work, he's obviously emeritus faculty here at UCLA, so he's like really cool. So that's kind of another reason why, again, our models aren't really kind of capturing that things. There's another important thing to note here, which is the fact that, we are collecting a certain number of features, right? We're collecting features that we think are relevant, but we're also somewhat limited. We can only collect certain features. There are features that we just can't collect. We just don't have the ability to do it. Or maybe we have the ability, but we don't realize that some of those features are relevant. And so we're trying to develop this model that's y equals mx plus b for your x, but there will often be times when I'm not capturing all the relevant x's. There are other exogenous variables out there in the universe that would sort of explain or capture sort of subtle shifts in y that I just simply am not capturing in my model. So, and last but not least, if you want to get purely highly philosophical, to what degree is the world actually purely deterministic? I mean, even in a hypothetical scenario in which you can capture every possible input to your model, is the world really purely deterministic, or is there maybe a stochastic element of it? Is there maybe on a quantum level something that does that? And what does free will and not mean in a world where everything is purely deterministic anyway? So also something to maybe ponder on a Friday night when you have nothing better to do. But it is very much what I studied in undergrad, yes. And you think I am subtly bringing that into this lecture. There is good reason for that. Okay, this is another, not only a Star Wars meme, but an original meme. I'm very proud of this one. So now that we have kind of set the stage and we've said, okay, well, I have my data, I have my labels, and the reality is the data presented will almost never kind of fully, perfectly reflect that universe for the reasons we discussed. We have to talk about the type of errors that our model can produce. And there's really two types of models. And your job as a data scientist is to balance these two errors. Because it's very easy to kind of, if you think about that scale, you're trying to find a balance between variance and bias. So variance is the first type of error. It's the idea that your model can be overly sensitive to these small, statistically unrepresentative fluctuations or outliers or things that really are not reflective globally, but just happen to end up in your particular data set. And if your model is overly sensitive to that variance, you will incorporate those outliers or noise into your training and result in overfitting. So I think the easiest way to look at this is to look at this in terms of this graph here. So we have this general trend of data here. You can kind of see this here. And we have this nice kind of, I guess, elliptical curve here that generally, if we want a line, we're going to want something that maybe looks like this, right? We already know that that's kind of where we want to end up, a line there. Overfitting is something where we have just worked our model to the max, where it is grabbing every slight permutation and variance and thing like that there. That just is just simply not the broader trend that we're trying to capture. So that's overfitting in a nutshell. And so, when I talk about dealing with, so that's really what this meme is about. When you kind of allow your model to continue training, to continue minimizing your loss function to the point where it has generated this, that's an instance where you've overfit and you've created a model that just clearly is not reflective of the broader trend. The contrast to this, the difference of this, is bias. And bias is the opposite idea. It's the idea that rather than trying to sort of accurately model that underlying trend in your data, you just kind of make a set of simplifying assumptions to your model that sort of produce a model that is just really not reflective of that underlying pattern at all. So if this is you doing too much, this is you doing too little. And so again, so this is variance, this is bias, and this is that trade-off. And your job as a data scientist is to end up somewhere in here. So I'm not going to play it, but I want to talk about bias, baby. Get a little vanilla ice going in our discussion. Yeah, I will spare you that. You can watch that on your own time. So quick note. So if we're dealing with bias, oh, it played. No, didn't want to play. Sorry. Okay. So if we're dealing with this problem, right, where we underfit our model, where we start off here and we just kind of like, okay, here's a line, I'm done, right? If we want to deal with bias, how do we deal with that? Well, we try to minimize our loss function, i.e., right, and we will get into that. This is what I want to cover, I think, more next week. But you sort of already know how that works. We define our loss function, something like maybe MSE or something like that. And we essentially train our learner, train our model to try and minimize that. So, right now, here our loss function is going to be huge, right? Because we are just getting massive error. And we want to continue training it until our loss function is essentially minimized. So that we will discuss in more detail next week, how that actually works, what the trade-offs are that, but just so you're kind of aware, generally that's how we deal with bias, is we just allow our model to train to minimize the loss function. So don't play, sorry. Okay, variance. Okay, how do we deal with variance? So variance is the opposite idea. So here's the idea that we have sort of allowed our model to overfit. And we have allowed it to kind of train, if before we weren't training enough, now we're training it too much. And so generally speaking, the way we kind of address that is conceptually, we try to put the brakes on our model. We try to say like, okay, we want you to train, but we don't want you to go crazy. We want to put a speed limit on our model training, right? So if you look at kind of this thing here so let's say this green is the hypothetical kind of maximum optimal model we can achieve. This is getting a little better, but it's still underfitting. This is sort of that nice optimal sweet spot. Pretty much we're there. At this point, we've gone too far. And yes, we have minimized our error. Yes, our error term has gone to effectively 0, but that is just terrible. So intuitively, if we want to kind of pump the brakes on our loss function, right? We don't want this visual here where your gradient descent function is just like not stopping. It is just going and going and going until you hit. Okay, these embedded videos are terrible. I'm never doing that again. But we want to kind of prevent it from reaching that point. We kind of have to sort of handicap it a little bit. We want to sort of stop it. And the way to do that is essentially, very simply put, we want to simplify the resulting equation. We want to say something like this is too complicated. If our function is too complicated, it's overfit. So we want to think about sort of approaches or strategies that we can take for simplifying that. And so then just kind of a note, we actually ask you to play around with different regularization strategies. So for instance, there's a point at which we say set the penalty to none. We're turning off your regularization. We're saying at that point, no, just run to completion. Whatever you were able to do, it doesn't matter how crazy or convoluted that resulting function is. We are perfectly happy with that. That's kind of what you were doing. Or if you set it to L1 or L2, you're defining different strategies for doing so. So now that we've said, okay, well, we don't want our resulting equation to be too complex, let's talk about how your equation can end up being too complex. What are sort of ways in which that would manifest? And the reality is we're really looking at two ways. The first is you could have a function that has the dimensionality of our function is too high. And so, we have just too many terms in it. So that might be one approach. The second approach may be coefficients, right? Maybe say that, okay, well, if for every feature I have an associated coefficient with it, then, if I'm dealing with very large coefficients, that will sort of cause those spikes and those sort of random arbitrary kind of jut outs that will sort of lead to overfitting, particularly if you've sort of weighed one feature particularly high based on some outliers. So if those are the two approaches that we can take to reduce the complexity, then not particularly surprising, there are two normalization strategies you can do that target each of those, and that's lasso and ridge. And this is something that we touch on in both the project, but also more significantly in the homework. So lasso or L1 So this is actually, so you kind of see this here, which is, and I'll get to actually this entire thing, but this, let me sort of help break this down for you. This is an example of your loss function. And this is your, and this function, does anyone know, just looking at this, what the loss function is? Like what that loss function is?
Isn't that ordinary least squares?
What? It is an OLS, but what is the particular loss function for it? So yeah, you are doing a OLS linear regression, but that particular metric.
L2, because it's squared.
Okay, good guess. L2 will actually be this term over here, so we'll get to that. But yeah, okay, in the chat, great. Courtney, MSC, yes, mean square error. So the way to interpret this, so remember, if your yi is your actual y value, and then your bxi is your sort of aggregated sort of sum of your quadratic term, that's essentially your actual minus your predicted, squaring it and then dividing by n. So you're taking the mean of your squared error. So this is an MSE function. So, and remember, our goal is to reduce this, to say, okay, whatever, I am going to run my learning model. And again, stay tuned for next week when we get into like what it means to run your learning model and actually try to kind of minimize this. But our goal is to run our learning model until we have minimized this overall term. But what I then do is I tack on these penalties, and either an L1 penalty or an L2 penalty. And an L1 penalty says, so this here is the sort of the weight that you assign to your penalty. So obviously, as you can imagine, the greater the penalty that you assign, the greater the magnitude of the penalty, the more effective this error term will be. So this one takes the sum of the absolute value of all these coefficients, multiplied by, again, that error term, and it adds that to your loss function. So remember, you're trying to minimize this loss function here, but then you have this term added on here. So now, not only do you have to minimize the loss function, but you have to do it in a way that also minimizes this penalty, or at least balances, right? There's a trade-off. If you do increase your penalty, you have to decrease your loss function by a greater proportion than that. So a lasso in L1 will take the absolute value of your coefficients and then just sum that up. Your L2, your ridge, squares your coefficients and then multiplies it by the penalty. So conceptually very simple. And if you think about remember when we were talking about like MSE versus MAE, sort of a similar dynamic there in that, in both of these, we're intrinsically dealing with how you handle negative values. But in this case, you're just taking the absolute value. Here, you're squaring it. And the results are very different. And a lasso at M1, because you're just simply taking, you're just summing up your overall terms, the result of this will be that it will tend to zero out features. It'll tend to zero out your features. Right. Oh, hang on a second. Can you help with that? Are you okay? Okay. Is this like, oh my God, that's so heavy. Guys, hang on a second, sorry. Oh my God, it's huge. You really be able to carry it? What?
No, I carried it myself.
Okay, I'm just gonna put this in the floor.
Dirty by it.
Yeah, I'll have to clean it. All right, sorry guys. So, okay, let me finish my thought here, and then I'll hop over to the chat. But yeah, so think about these as being sort of kind of adding breaks. Okay, sorry. Let me sort of talk through what these do. So here, by taking the magnitude of this, you're effectively treating all coefficient values equivalently. And so it doesn't matter if I'm going from a 9 to an 8 or a 2 to a 1 or a 1 to a 0, any reduction in my coefficient will result in lowering my L1 score, right? It treats them all the same. And because it treats them all the same, by nature, it will end up zeroing out more features. And that's why a lasso thing will tend to result in sparse features. Now, it doesn't automatically do it. It's not necessarily an explicit goal of the model, but by simply treating every feature the same, you'll find that it'll tend to zero out more of your features. A ridge regression, so that's why a lasso penalty, the result of it will be that it'll result in sparser data sets because you've zeroed out more of your features. For a ridge, because we're dealing with squared values, that disproportionately penalizes higher or magnitude coefficients. So there, going from a 4 to a 3 or versus going from a 10 to a 9, there is a dramatic difference in terms of your penalty function. So there, it will almost always bias itself towards reducing the overall magnitude of the term, but it won't necessarily zero it out. And particularly when you get to fractional, when you go less than 1, the effect of zeroing that out, effectively at that point by squaring it, you're actually reducing the magnitude of the coefficient. So for that reason, a ridge term will tend to lower the magnitude of your coefficients, but won't zero those out. So that's why these work differently and the result is different. Now I should mention, this is also, you can do a combination of those. And I think we talk about that in the homework. And that's actually a thing called, I think it's called Elasticsearch even, but that's where you use both L1 and L2 in concert. Yeah, so sorry, let me just quickly do that. Normalization and regularization are analogous, are equivalent. Yes, both of these, the goal is, again, going from this thing where you have this crazy, quadratic term that is just all over the place to something that is a nice sort of smooth function. Yeah, so normalization, regularization here are used interchangeably. And so, and this is kind of an interesting approach where you can do either just lasso, ridge, or you can do some permutation of both. And that's what you can see here, where you're actually applying both to your model. And kind of one of the interesting things to do. And there was even, I think, a good question in Piazza about this, about why you would want to use one or the other. And Orpaz, I think, gave a great discussion about that, where like, if you think you have a lot of collinear terms, if you think you have a lot of unnecessary features in your data frame, something like a lasso where you zero out your features is going to be great. On the other hand, if you feel like your features are generally important, you don't want them zeroed out, but you do want to reduce the overall complexity of your term, something like a ridge would be a really powerful approach. And maybe a balanced approach like this may be good, where you kind of want to do both. You think maybe you have some extraneous things, but you also think the relative magnitude needs to be reduced, and you kind of want to take them in concert. Yeah, so that's normalization. And then so Daniel, to your question, it's in a way like adding noise to our thing, but I think the way that I think about it is if my gradient descent or whatever function I'm using to kind of minimize my loss function is sort of speeding towards this puts the brakes on it. This says, okay, it's okay to try and minimize this, but you have to do it in a way that doesn't either cause the total magnitude of your coefficients or the squared sum of your coefficients to increase. And that any strategy you take has to balance those. So in a way, it's like kind of applying the brakes to your learning model. So I think that's actually all the formal material that I prepared for this week. So let me pause there. Any questions?
Yeah, I have a question about project 2.
Okay, yes, let's do it.
Yeah, so midway, we basically set the parameters for logistic regression,
Mhm.
and you ask us to set like SAG, max iter 10, and penalty none. And we run into the expected warning of the model not converging. So then you ask us to fix it. When you ask us to fix it, are we allowed to change any of the parameters you originally asked us to input, or are we expected to add on a new parameter?
Oh, great question. Okay, yeah. So there specifically, by setting your max iter to 10, you have effectively broken it. So fixing it just, I mean, not much of a spoiler, but yeah, just change that.
Okay, yeah.
So yeah, I'm glad you asked to clarify that. Yeah, you don't have to try and mess with any of the other parameters. You just like you don't have to keep the parameters that I told you to say, because what I did effectively broke the model. So I want you to then just try and fix it. Let me explain why I broke it and how what you did fixes it.
Well, I have a follow-up question to that. What if we found a way to fix it without changing any of your parameters? Is that still okay?
Oh, well, yeah, heck yeah, that's okay. Yeah. I mean,
Cool.
as long as you know, just describe what you did, but yeah, that's amazing if you get convergence in 10 epochs.
I also have a question on project 2. It's on the part where you say to explain the two solvers approaches, linear and SAG.
Yeah.
I'm wondering, do you want like an in-depth explanation of how they actually work to optimize, or do you just kind of want what they're better for? Or...
Yeah, thank you for asking that, Ryan. So no, definitely don't go overboard with that. I just want a few sentences each. The goal of that exercise is really just to get you to kind of understand that those parameters are out there and start doing some, like, just look up the documentation to say, oh, okay, that's what that model is good for. You know, that generally how that model works and what types of data it tends to work well on. So,
okay, that makes sense.
Yeah, but
on the
we're really not
documentation,
looking for more than a couple sentences. Like, I don't expect you to be an expert on SAG. I don't want you going and looking up the literature for that or anything like that.
Okay, great. Thank you.
Yeah, thank you so much for asking that. Okay, so Courtney in the chat's got a question. Are we evaluating performance based on F1? So, okay, so great question. So for this one, we obviously are asking you to generate all 4 metrics, you know, accuracy, precision, recall, and F1. We don't, yeah, because I do ask you in the end for what to choose your best performing model. So because we don't specify which one to use, I think you're okay if we use F1 or accuracy. And you could probably make an argument like you are that F1 is probably the better choice. But yeah, you can go either one. And that's a general rule. If we haven't told you like you have to do a certain thing a certain way, if you just choose to do it in a way that makes the most sense to you, that's inherently defensible, then that's perfectly fine. So yeah, so then there's also just a direct message asking about F1. F1 is usually the better metric to go with. And so we had sort of talked about that a little bit last class. The reason F1 is better is because that's much better in dealing with class and balance issues. So, you know, we had given the example with like credit card fraud, where 99.99% of your instances will be a true negative, but you're really, really interested in those 0.001% of actual fraud cases. And F1 is really great at getting at that class imbalance. So yeah, I will say that as a general rule, we almost always use F1. When we're working with data, we'll almost always use F1 as a metric. So yeah, and so, okay, great question then. So accuracy can still very much be a good measure, particularly if you really care about true positives and true negatives. You know, if the classes are balanced and you do care about the overall performance, and you care specifically about something like true negatives or true accuracy, can be really helpful. So Again, it's one of those things where you as a data scientist, part of your job is to define the goalposts and to define what success looks like. And part of that is understanding what metric works best for you. So there will be some models, some scenarios in which accuracy actually may be a better approach. And again, if classes are balanced and you care equally about, so here's what I say. Imagine if your classes are balanced, you have a 50-50 thing. A F1 score just looks at precision and recall. It just looks at your essentially just looks at the positive classes. It doesn't care about the negative classes. It really doesn't care how you do there. It just cares about how you do with the positives. So if you care about both, if you say it's important to me that my model gets both the positives and the negatives correct, and these cases these classes are balanced, then accuracy is the way to go. An F1 score will actually not give you the information that you want. So yeah, just, again, just another thing, like you as a data scientist kind of defining what success looks like and understanding kind of what ultimately sort of makes a model optimal. Yeah, great question.
So I kind of understand what SAG is, but I looked into linear and I can find like a couple headline descriptions, but I don't understand it quite as well. And I'm just wondering, like, it might be not really what this course is focusing on, but I was just wondering, like, would you or the professor eventually cover it, like linear? Because it sounds familiar to gradient descent, but I'm suspecting that it does something slightly different.
I have to actually look up the documentation myself. I'm not aware of it, and I'll tell you for sure it's out of scope for this course. I mean, let me put it this way: what we would cover in this course is we would talk about gradient descent. We would talk about how it works, but we wouldn't get into like the specific permutations of different approaches to it.
Yeah.
So, and that would be out of scope. But if you're interested, I can try and dig up more information specifically on it. But
yeah, because I just found like SAG as the counterpart was like really interesting because this was my like CS146 class, even though it did cover the theory behind a number of approaches, it didn't cover SAG. The closest it did cover was like SG. It was interesting to hear about SAG.
Yeah, we're going to cover. So I actually have some material on both stochastic descent, and I have some material on stochastic average gradient. So yeah, we will talk about both a purely statistic. So we're going to talk about like a batched versus a purely stochastic versus some aggregated thing, and SAG being sort of an interesting hybrid example of that. So, but I think the goal for this course, particularly around gradient descent functions, is going to be to kind of understand generally how they work and understand the different approaches you can take and the trade-offs with them. So again, the idea more generally that you would be sort of empowered then to go out and learn about specific, gradient descent approaches and think about what might work for you, what might not, but not necessarily offhand be fully expert in any of them.
I had a question about the penalty terms we were going over.
Yeah.
So I understand that the purpose of them is to kind of push the coefficients down and prevent overfitting. What I'm kind of confused about is how does adding those penalty terms to the loss function actually do that? Why does it actually push down the coefficients?
Yeah, great question. Okay, thank you for asking that. Let me pull up this slide again. So if this is so we have our loss function here, and the goal of our whatever our gradient descent model is to minimize this loss function, and it will run until it has converged, at which point it has sort of minimized this loss function, saying this is the best I could do, this is the minimal possible value I can get. And again, hand waving on that next week. What we're essentially doing with this is we're tacking this on to the loss function. So our goal is still to minimize this total function, but the only difference here is that now not only do I have to minimize the loss, but I have to minimize the loss by also not allowing my normalization, my regularization term to kind of to grow out of bounds. So it's still a minimizing function, but it's a minimizer where you minimize this plus this. And the idea here being that like if the overall kind of value of my coefficients is, you know, greater than this, then, you know, my impact, I will no longer be minimizing this term. And in fact, for every sort of optimizing step I take, I have to weigh the value of increasing, you know, the magnitude of my coefficient against the resulting sort of reduction in error. So does that kind of help think through how a normalization helps that?
Yeah, that really helps. Thanks.
Okay, awesome.
I have a question about the homework.
Yeah,
cool.
absolutely.
So number one is about like using k-nearest neighbors for classification. And I know on the syllabus it says that we may cover that next Tuesday, but should we like, can I ask you a question about it or should I just wait for the lecture?
Yeah. Let's ask it now. Yeah.
I'm not really sure how to draw the decision boundary because it like intuitively I feel like I would need to like be given a point and then I can say, okay, now I can look at like the closest neighbor or like the three closest neighbors. So I'm not sure how to draw it like a general decision boundary like the question seems to ask.
Yeah, okay, great question. So let me pull up an older slide that I have on that will hopefully kind of help to visualize it. But I will just say, just as a quick overview, that you know, we don't necessarily expect you to be like perfect in terms of the decision boundary you do, as long as it generally is notionally correct. We're not going to like say, oh, well, you were marginally fractionally off. So let me kind of just show you this slide. So this is from week 3. So so this was KNN for regression, but so part of what you're doing when you're, but it's essentially the same idea. What you're doing when you're sort of plotting a decision boundary for a KNN is you're plotting the sort of the sphere of influence, if you will. So let's look at this orange line here, the one nearest neighbor thing. So here, you know, it's okay. So everything from here to here, here to here, obviously this is the nearest neighbor. So, and let me just say this will be a classification. You'll use this for classification too. So for one nearest neighbor, whatever this class is, wherever this class is, that's going to be the class I assign. Then suddenly this is the point at which this becomes the nearest neighbor. So my thing jumps up here. And then this is the sphere of influence for this guy right here. And so any value here, I assign that class. And then so on and so forth and so on and so forth. And so, and when you're looking at, so let's look at the two nearest neighbors. So here you have, rather than, now you have to look at it not as like the sphere of influence for just the one item, but where the shift happens in terms of the two nearest neighbors. So in this case, these are the first two, and at some point, it gets further away from this one and closer to this one. And so at that point, these are the two nearest ones, and then it becomes an average of that. And then for a little while, those are the two nearest neighbors. And then suddenly, this becomes the nearest neighbor, so then it drops down to being the average of these two. And then suddenly this becomes the nearest neighbor, and so on and so forth. And so you're essentially asked to do the same thing for that trend line. Your goal is to kind of, the way I would recommend doing this is figure out where those inflection points are. Figure out where it shifts from one to the other. And there will be sort of a series of discrete points along the way where effectively it kind of moves from being closer to one to being closer to the other. And then there's that series of handoffs. And then once you have those points, I would just connect those lines. And that would be your decision boundary for a KNN.
Okay, so it's just the inflection point where it switches from one to the other. Okay.
Exactly. So that's the approach. When I solved it, that was the approach I took. I essentially looked for the inflection point where, again, there's that shift in terms of that sphere of influence. And then once I had that, I just kind of I had those series of points. I just filled in that dot, and that was my inflection line.
So
That was
just
my
for
decision boundary.
clarification on kind of what you're saying, if you had 3 points that were obviously like the closest and it was like k equals 3, you would basically almost like plot a point or put a mark that was like equidistance between those 3 points, and that would be the point that your line would then go through.
Yeah, it's or pretty much the point at which, so to use your k equals 3. So like, let me share this again, just as a, so for your k equals 3, just an example. So here, right? So if I look at this line sort of progressively, these are obviously going to be my first 3. And so, oh, I don't even have a 3. Okay, so it's 4 nearest neighbor. So obviously, but there will be a point at which, if I'm looking at this sequentially, where this line takes over from this line, and there will be an adjustment. So for me, it's just thinking about, okay, well, where does this take over? Where does that happen? So maybe roughly like around here. And so that's going to be my first inflection point where, okay, and then I just take what the average of those are, and I say, okay, well, that is, that's the inflection point. Where up until that point, it was, let's say, maybe like something here. And then at that point, it becomes, let's say, something more around here. And then I look and I say, okay, well, at some point, this one becomes the next one. So this one is going to take over for this one. So now just figure out at what point that is, and then just take the new value and adjust it down.
Okay, so as long as we have like just like a decent eyeballing of it, like that's okay.
Exactly. Yeah.
Okay.
It's just going to be about a decent eyeballing. And again, just work through it. I think the easiest way is just to work through it. Sort of just look at this as a linear progression, and just start out and say, okay, well, here's my k equals 3. At some point, just working through it, this will become my k equals 3. And then this will be my k equals 3. And then this will be k equals 3. And then this, right? And then at each point, figure out what's the point at which it switches from this being k equals 3 to this. And then just assign the relative value shift to that.
Cool, thank you.
Yeah, absolutely. And yeah, just eyeball it. It doesn't have to be precise. You just look at it, you say, okay, well, the average distance is roughly here. This is the average between them. So it'll be like roughly there, and it'll go from here to roughly here, something like that. And yeah, you just eyeball it. Okay, so what else is going on?
Lionel, I had a quick question on the pipelining for our project.
Mm-hmm.
So it's said to handle categoricals however we wish and to scale our numeric features using the standard scaler.
Yeah.
But somehow I found that if I just scaled every feature using the standard scaler, all of my statistics improved. Do you know like why that might be the case?
Yeah, so great question. So generally speaking, so the reason why you scale your numeric features is obvious, right? Because you could have for a numeric, you could have just vast different range in terms of features. You could have values that are fractional, and you could have values in the millions. And so obviously it's important for numeric to do that. For categorical, theoretically, your value range is more constrained, but it's not completely constrained. And particularly if you're doing integer, categorical. So let's say you have categorical, let's say you have a feature with 10 values. So then, and assuming you don't want to hot encode it. So there, your thing will be 1 to 10, right? And then if you have scaled everything else, so let's say you use, so I think there's different types. A standard scaler, I think, takes a mean value of 0 and a standard deviation of 1 and -1. I think that's what a standard scaler does. So if all of your numeric features have been reduced to essentially a -1 to 1 range, and then you have that one categorical that's got values, 1 to 10, there's still going to be a sort of a feature magnitude imbalance there, right? And so the result is that while generally the degree of distortion is much lower than for numeric, it's still there. And so, you're not wrong to then say, I'm going to treat all of my features uniformly the same way. I'm going to put all of them through that scalar such that my categoricals will be scaled down to the same value as everything else. So it's definitely not, you're definitely not wrong to potentially scale your categoricals as well. And it's also not surprising that your performance might improve if you do that. And guys, hang on. I'm going to close the window because they're mowing the lawn outside. Okay, how's it going?
Going back to the KNN problem, so just to be clear, we're not reclassifying any of the existing points based on all the other ones. We're like assuming we have a new point we're classifying based off the ones we're given.
Perfect. Yes, Courtney, you're exactly correct. Yes, that's exactly right. And so what you're doing is you're saying theoretically, where would my decision boundary be if I'm given a new point? So if my point fell above that line, it would be classified the one class, and if it's below that line, it'll be classified the other class. So yeah, thank you for clarifying that.
And then I also had a question on the homework number 3. I guess when it's asking about the general expression or like the relationship between the features, is it just asking us to like rearrange the equation? Or?
Yeah, I mean, literally that's all it's asking you to do. Yeah. You're literally just solving you're just isolating that particular thing in terms of everything else. Yes. Yeah, it's one of those questions that I think is deceptively simple, but it's written in a way that seems more complex than it is.
Okay, and like the same thing for 3B, where it's like, what's the relationship? And it's just the equation.
Yeah, I mean, that's exactly it. You're literally just restating it in terms of the thing. And then you're asking for B, A versus B. Yeah, so A is just asking it for the generalized term. So in terms of an unspecified number of features, and then B says, well, if you're given, if you're specifically given 2 features, X1 and X2, just write it in terms of that thing. So yeah, it's conceptually not crazy at all. It's just written in a way that suggests that.
Okay, thank you.
Yeah. So Daniel, to your point, I think that was for us, that was the potential trade-off. And that when you're looking at, so there was a question about one hot encoding and specifically about states. And states is that iffy thing where it's like, on the one hand, those are clearly not, there's not an ordinal relationship, and clearly we want to do that, but it's a judgment call, and 50 to me seemed high. Again, because you're particularly for, you're adding 50 discrete features to your data frame, which seems like a lot to me. But, again, I think there's a bit of a value judgment there. And ultimately what I would say is you would have to decide how important state is. Like there's that trade-off. If you think like state is critical to your model, and then you're like, okay, well, I'm willing to tolerate adding 50 features to my data frame if it means I get to model the relationship between each state and the thing, But if it's the kind of thing where it's just part of an address and it may have some impact, but it's likely a marginal one, then, you know, probably the cost isn't there.
So I was thinking of it like, since we were doing like price prediction before and stuff of like Airbnbs and stuff, I was
Yeah.
like, oh, well, like what is the housing price in California versus Tennessee? And what is, you know, and if you're trying to pick housing prices, then state would matter and could help you get a better prediction. So, and I don't know. I mean, I do get that 50 is like a fair amount of features, but it's nowhere near like when we did the groups like Manhattan or whatever. Like if you did the individual, like that was like a much larger blow up of data. So I don't know.
Yeah, so I would, okay, so specifically to that question, I think if you submitted a regrade request to that, I think, and just explained your logic, I think you would have grounds to get points back for that, because it is a matter of interpretation. And again, I think just in general, it really is about you weighing what you perceive to be the importance of that feature in terms of your model against the risk that it imparts by potentially overfitting. And so I guess when we wrote the solution, we looked at it and said, generally, probably the risks don't really outweigh the rewards. But again, if you were in the course of kind of working through it, you came to a different conclusion. I can't fault you for that. So I think you should get points back for that.
Okay, cool. Thank you.
Yeah. Because again, there isn't a right or a wrong answer to that. And, you know, I think your example is a good one where state does matter. If you were looking at real estate prices, the state the property happens to be located is pretty important. And there you say, you know what, it is important enough for me to model the individual relationship of state against price. So yeah, and you wouldn't be wrong for making that decision. And there's no like hard or fast rule that says, you know, any feature expansion above X is a problem. It really is just about that trade-off.
Okay, cool. Just for curiosity's sake, in general, even though there's no hard or fast rules, when do you become apprehensive of a data set where you're like, is there a certain number that you're like, oh, this is going to add, like, is it 20 features or 10 features, or is there a certain line that makes you kind of go, oh, I should be careful?
I would say double digits is where I start kind of thinking about alternatives. And that's not a hard or a fast rule, but that's where I start saying, either is there a way to consolidate this, or, you know, is this important enough as is? But again, that's not a scientific thing. Like, why is 9 okay and 10 is not? It's just once it goes into double digits for me, I'm like, okay, is this, you know, is the, what's the expression, is the bite worth the squeeze? However that goes.
The juice.
The juice, that's it.
Yeah.
Juice worth the squeeze.
Fair enough. Cool. I actually like the saying. I use it sometimes. So.
I have another question just in general. Is it better to use like the stratified split for smaller data sets?
You're asking, would it make sense to use it?
Yeah, instead of just like a regular split.
It would, and actually, okay, so well, sorry. Firstly, I do have to acknowledge Brandon putting up Star Wars in the Zoom, and so I thank you for getting in the spirit of May 4th. That is greatly appreciated. But Courtney,
I didn't even see it.
Huh?
I didn't even see it. Is it his background, or where?
It's his Zoom.
So you can
there we go.
Yeah. So if you
I just had it on speaker view, so I was missing the good stuff. Sorry.
So yeah, but so Courtney, to your question, so you would use, so the short answer is yes, it definitely would be worth considering doing when you have a smaller data set, specifically because, or when you have a highly imbalanced class in which you want to make sure all values are represented proportionally. So, you know, the whole idea of doing that stratified split, of course, is like the idea that says, I want to make sure that both my training and my testing cohorts have data from this particular feature in proportion. So I want to make sure that these are proportionally represented. And I think the best example was from that New York data set where you would stratify split by borough. So you would say, you know, I have properties from Manhattan, Brooklyn, Queens, Bronx, Staten Island. And I want to make sure that both my test and my training data sets have all 5 boroughs represented in statistical proportion. And so, and the reason that a smaller data set, you have a bit more of a concern about that is because oftentimes there you may only have a few instances of a particular feature value. So you may only have a handful of Staten Island properties. And so if you haven't stratify, shuffle, splitted that, then chances are those will just get bundled up into your training data and won't show up in your testing data. You know, if you're only taking 20% of your data frame. Conversely, if you have a large data set, but you happen to have a particular class value that's highly imbalanced, so, you know, maybe you have thousands of features, but it just happens to be that you have a dozen Staten Island properties, you may also want to do that and say, you know what, even though I have only a handful, I want to make sure these are represented. So would it, so then, okay, so great question. So would it ever be a bad idea? So I wouldn't necessarily say a bad idea, but I would say it's a targeted approach in that certain classes it isn't as important that you make sure that they're fully represented. You know, I think that's a target that you may want to strategically employ. You may want to say, is there a particular class or set of classes that are, you know, critical to my model and I want to make sure are included? But if there's others, you know, then I'm just not going to worry about all of them showing up. So, you know, I don't necessarily think you would be wrong to do it, but, well, actually, no, let me take that back. A reason why you might be wrong to do that is it enforces a distribution that could be arbitrary and not relevant to your data. So, you know, by forcing you to maintain that proportionality, you're essentially saying, this is the proportion that I expect my data in the real world to follow. And that may or may not be the case.
Okay, that makes sense. Thank you.
Yeah, great question.
I'm really sorry. Do you mind repeating that? Because I had a distraction here in the house.
Yeah, sure. From which part?
Just you said it enforces. I try and take notes on everything you say. So.
Oh, please don't. Half the time I don't even know what I'm saying.
Okay, so it enforces it
enforces a distribution in values. It basically, when you do a stratified shuffle split, you're essentially saying that the values that I see here and the ratio of values that I see is representative of the universe of data. Is essentially what you're saying. And you may not want to kind of impose that ratio on things. You may not want to say this is how it is in the real world. Because, you know, those values, it may be a completely different distribution, or, you know, the distribution may not be all that relevant in terms of your real thing. But by enforcing that, you're essentially saying like it has to be a certain way.
Okay, cool. Thank you.
Yeah, absolutely. All right, what else is going on?
Lionel, what's your favorite Star Wars movie?
Ooh. Well, I mean, we can just get rid of the entire prequel and sequel trilogies. Those are just not viable.
Good choice.
As options. I feel like everybody says Empire, but I was never a huge fan of it. You know, I mean, just A New Hope, like it was just such a solid entry. And what sequels? Yeah, I gotta go episode 4. You know, I haven't even watched the last one. I couldn't put up with it. I was just like, I can't believe what they've done to it. I love it's funny because I love what they did with Mandalorian. I love the show, but the films were just such
Okay, so I have a question about that then, because I can't even remember the name of it offhand, but there was that one film that was a one-off that wasn't like a part, it was like a prequel to,
There were two,
like,
Solo or Rogue One.
yeah, I don't remember. It was one of those. Everybody dies at the end.
Rogue One.
Okay, what did you think of that? I really liked that
I
one.
loved that film. That was amazing. Amazing.
Well, it's because they didn't need to like fit into all these tropes or anything. They just they like could set up the story, and it wasn't like, yeah, it was good. I liked it.
Yeah, you know, it's interesting. You'll see this with a lot of when you do postmortems on a lot of like film or television products. One of the obvious ways in which kind of people make mistakes is that they're too ambitious with the plot. Like they try to do too much. They try to either like jam too many subplots, B stories. They try to sort of overly convolute the plot. And oftentimes the best stuff, the best work is the type of show or the type of film that knows what it is and just sticks the landing. It doesn't get overly ambitious. And I think Rogue One is a great example of that. Like it knows what it is. It knows what it's trying to do. It's not trying to shoehorn a bunch of things in there, and it just does it well.
Yeah, I really like that. I was pleasantly surprised because based on some of the other films, I was not expecting much.
Agreed. Like an example I always give of that, and I'm not even usually a fan of the genre, but have any of you guys seen the show Bosch? It's on Amazon Prime.
No.
It's worth checking out. So it's this sort of classic cop procedural thing, and it's sort of a long arc story. So it's not episodic. It's long arc, and it follows this LAPD detective. But to me, it's just a great example of a show that like is great to watch because it doesn't try to be more than it is. And within the genre, it just nails it perfectly. And I will say it's also fun because it's one of those shows that like there's been this whole thing about like how Los Angeles is represented in the movies and you know Los Angeles's role in things, and more often than not it's kind of this Los Angeles is part of like it sort of collapses into the background. It's not a real presence. It's not a real character because it's just a generic background setting for anywhere else. But what's cool about Bosch is it makes LA kind of at the forefront of thing, and every season is sort of a different area in a different neighborhood, and I think that's like a really cool aspect of it. So for what it's worth. But yeah, but just a great example of a genre piece that gets what it is and doesn't try to be more than that.
There's a lot of shows that were trying to do that after Game of Thrones.
Yeah.
Like a lot of copycat shows that, like, what's that new just came out? I haven't seen it, but they pumped a bunch of money into it, and it's supposedly horrible. It's a new fantasy series.
Which I guess streaming service?
No, I don't know. I pretend that I still do things for fun anymore. I just do school. So.
Don't we all? It's so sad. I put in either the Secret Bruno, the other one. I did a thing like not that you guys have any time to read, but assuming you did.
That's actually, thank you for the reminder. I need to get my.
Yes, for
Secret
those of you
Bruin
doing
gift together.
Secret Bruins, I'm going to send out a reminder on that maybe tomorrow.
How many people participated? Did most of the class join in, or?
Sadly, most of the class didn't. We had a nice cohort, but not that many.
I remember I thought a lot of people, a fair amount at least, of people did it in 180.
They did. I would say close to half the class did in 180, and then when we did it last quarter, we got maybe about a third of the class, and now. What's the enrollment in this class? Is it 120? Or is it 160? I forget.
I honestly don't remember.
Or is it 180? Regardless, we had about 20 people sign up. So clearly not even getting close to those numbers.
Well, if you did it, now you might know who your Secret Santa is. So, or Secret Bruin.
Your secret Bruin.
Yeah.
Brandon, adding Kermit to the Star Wars was a nice touch. Now, I assume you didn't do that personally, but.
So I know this isn't straight like film TV media, but it's a classic game, Knights of the Old Republic, Star Wars Knights of the Old Republic. Have you?
I never got into the gaming thing about it, sadly.
that okay, so I'm not like big on, I think a lot of like genre, or like when they try and make a game after something, it's like, okay, whatever. But that game is like that's what got me into Star Wars. Like I didn't care as a kid. Yeah. And then I played that and I was like, oh, it's like the world is so much more interesting than just Luke Skywalker. Don't get me wrong, I don't have a problem with them, but
Knights of the Old Republic. Interesting.
Yeah. Kotar.
Okay. Neil, apparently you're a fan of it too.
It's an amazing game. It's you know, basically what they did is they kind of it doesn't follow Skywalker's story at all. It really and it delves a lot more into like the background of like the Sith and stuff. You get a lot more like history and like world context. And this might put some people off, but for anyone who's played Dungeons and Dragons or whatever, they basically took the mechanics of the board game, the tabletop Dungeons and Dragons game, and that's what's like running under the hood Star Wars.
Oh, wow.
And but yeah, it's really fun.
What genre is it? Is it like is it a first person shooter? Is it like a role playing game?
It's an RPG.
Okay, it's an RPG.
Yeah.
Okay.
Yeah.
Cool.
So,
I'm gonna have to check that. And it's available on PC, I assume.
yeah, you can probably get it for like $5 nowadays. Like it's I mean, it's so old. So maybe today especially is probably on sale.
So Lino, if you want to earn some Twitch subs, you know what you have to do now.
Exactly. Forget about my YouTube personality. I'm going to start my Twitch streaming.
You got to beat Yolfson.
It's true, man. I got to diversify my platforms. That's the key for influencers these days.
I have a random question for you about your YouTube stuff. Do you keep your, like, I know obviously it's like unlisted, like all the stuff for class or whatever.
Yeah.
But is it still up there? Like, can we go, like, if 2 years later I'm like, oh, I remember Lionel had some really good information about
talking about recording.
Like,